All right, so this is going to be Unit 7.6. Now we're going to take all the information that we've been learning about exponential functions and log functions and all the different properties, and we're actually going to put it into use because now we're going to use all this stuff to solve log and exponential equations. It's going to be several different types of problems. Some of these are not going to be so easy, so they're going to take a little bit of time, but if you take the time and just be really careful, we can get through these. All right, so our first example is going to be to solve the equation 2 log base 5 of x is log base 5 of 9. This is one of those circumstances where all I have on one side and the other side of the equation is a log. They both have the same base, so we can actually try to solve this. If they didn't have the same base, we probably would not be able to solve this equation, at least not without using a calculator. In this case, what the idea is, we want to try and make it so that all I have is a log here and a log there. Remember the property that says I can bring the exponent up and make it, I can bring the coefficient up and make it the exponent of the argument. So that's what we're going to do. Once we do that, what I have is log of x squared base 5 equals log of 9 base 5. I have two logs that are equal to each other, according to this statement, both with the same base. If that is the case, the arguments must be the same. They must equal each other. Otherwise, this is a false statement. So what that means is I can basically say, okay, x squared then has to equal 9. Since I have the log base 5 here, the log base 5 here, it means that the arguments must be the same because it's an equivalent statement. So then we just go ahead and solve x squared equals 9. Take the square root of both sides, and you end up with the positive and negative 3. Because we took the square root of both sides of an equation to solve, you must include the positive or negative. Because this is a log equation, you must check your answers. If I were to plug positive 3 back in for x, no problem. The domain of logs is that you can take the log of any positive number. You cannot take the log of 0. You cannot take the log of a negative number, which means that the negative here is extraneous. Because if I plug negative 3 back in for x, I'm now trying to take the log of negative 3. That is not going to work. It's not defined. So my actual solution is x equals 3, or in proper bracket notation, it's just the value 3. And that's it. So if you can get it to the point where you just simply have one log equals another log, then you can make this work, as long as the bases are the same. Let's try another example. We'll now have the log of x plus 6 base 5 plus the log of x, forgot the plus in there, plus 2 base 5 equals 1. This one's a little bit different. If I could subtract one of these two logs to the other side, move it basically to the other side of the equation, and all I would have is a log equals a log, that would be great. But I can't get rid of this 1 that's sitting over here. I would have 1 minus one of the logs. So I can't really do what we just did in the previous problem. But what we can do is we can make this one single log by condensing it. I have a plus sign here, which means that I can condense this down to one log, base 5, by multiplying the arguments together. So I'm going to put a big bracket here because we're going to multiply x plus 6 and x plus 2. That is the log of that entire thing, and then that still equals 1. So let's simplify this a little bit. Well, you don't really have to do that here. As a matter of fact, you know what? Now that I'm thinking about it, let's not simplify it yet. We're going to have to eventually, but we're not going to do it yet. What I have is I have one log on one side and a constant on the other side. The variables are in the argument of the log. If I want to get the variables out of the argument of the log, we talked about this in class as well, you need to create an exponential function. You need to change this into an exponential function. So I'm going to take 5. Remember, the idea is 5 raised to that. So 5 to the first will equal the argument. So it'll be 5 to the first power equals the argument, which is x plus 6, x plus 2. So now we're going to go ahead and simplify some things. 5 to the first is just 5. We're going to FOIL out the right side, so that's going to give us x squared. Outsides will give us 2x. The insides will give us 6x. Adding those together, we'll get 8x. And then the last times the last will give us plus 12. It's a quadratic. We're going to go ahead and get one side set equal to 0. Since pretty much everything's on the right side, I'm just going to subtract the 5 on both sides, which will give us x squared plus 8x plus 7. And if this is factorable, then we'll factor it. If not, quadratic formula or some other method. This one looks to be factorable. And it looks like we're going to get x plus 7, x plus 1. Which means that either x will equal negative 7, x will equal negative 1. Once again, you have to go back and double check your answers. If we were to take negative 7, because that was my first one, and plug it into the original x's, it doesn't matter which one I plug it into. Negative 7 plus 6 is negative 1. I can't do that log. I can kind of finish it right there. I'm like, okay, that's done. If I had plugged it into the right side one, do negative 7 plus 2, that's negative 5. I can't take the log of negative 5. This is out. It's extraneous. Just because your answer is negative, however, does not necessarily mean it won't work, because negative 1 does work. If you plug negative 1 in here, sorry, it's too many arrows. If you plug negative 1 in here, that's negative 1 plus 2 in parentheses, that's positive 1. I can take the log of that. If I were to plug negative 1 in here, that's negative 1 plus 6, that's positive 5. I can take the log of that. Negative 1 is your solution, because it does work. And really, that's what you're checking. You're checking to make sure that this actually is something you can take the log of. So you're checking to see that it's going to be in the domain of the actual equation. You can definitely try to check to see whether the values work out. Sometimes it's going to be a lot easier to do than others. This one would work out well, but sometimes you won't be able to do it very simply. All right, so there's our solution to that one. Negative 1, that's the only solution. So again, condense the logs in that case. Since I have 2 logs on one side and a constant on the other, condense it and then change it into an exponential. Okay, let's try one more example. Well, not one more, there's going to be several more. But this one's going to change things up just a little bit again. So we're going to have the natural log of x equals the natural log of x plus 6 minus the natural log of x minus 4. So this one's different in the fact that we've got 3 logs. They're all natural logs, which means the base is e, which is why you don't see it written there. But you've got 3 different natural logs. There's no constants anywhere. So I can't just condense and then change into an exponential. But we can condense. The right side, 2 logs are being subtracted, which means that they can be condensed into 1 log, and the arguments will be divided. X plus 6 over x minus 4. The left side just stays the natural log of x for right now. Now what we have is basically the same kind of concept that we had on the very first problem. I've got two logs equal to each other with the same bases. Since that's the case, I know that the arguments must be equal to each other. So in your own mind, sometimes people are like, oh, I'm just canceling the logs. You're not really canceling the logs. We're just realizing that since these two logs have to equal each other, the arguments must be equal. So we're just setting the arguments equal to each other in order to solve the problem. We are not canceling any of the logs out. So please do not scratch out the log and say, oh, we're just canceling. It's not what's happening. Now we can solve for x. In order to start solving for x, we need to get the x minus 4 out of the denominator. So we're going to multiply it on both sides, which will then give us x minus 4 on the left. The x minus 4's on the right will cancel out when I multiply it by x minus 4 and leave x plus 6. So distribute on the left, x squared minus 4x equals x plus 6. Once again, this has formed a quadratic. So I'm going to get everything to the left-hand side so I can set one side equal to 0. So we'll subtract x on both sides, which will give me minus 5x. I'm also going to subtract the 6, which will give me minus 6, and that makes the right side equal to 0. Again, try your best to factor. It looks like this will factor. So that's going to leave us with x minus 6, x plus 1, which means that my values would be positive 6 and negative 1. And again, let's go ahead and make sure that we don't have any extraneous solutions. X equals positive 6 plugged into all three of the different original logs is fine. It's going to give me positive values for all my logs. We're good to go there. X equals negative 1, however, in that one right there would be a problem. Actually, it would be a problem in this one as well. It would not be a problem in the middle log, but all it has to do is be a problem in one, and we can't use it. So x equals minus 1 is extraneous. We get rid of it. My only solution is positive 6. All right, if any of these examples are going a little bit too quickly, I strongly suggest going back, kind of rewinding, pause it, whatever you need to do to kind of get the gist of these things. Watch it again if you need to. All right, those have been log equations. We can also solve exponential equations in a very similar manner. So if we have 2 to the x equals 5. What this is really saying is 2 to some power has to be 5. Well, we know that 2 squared is 4, 2 cubed is 8. So this is going to be, again, it's going to be a number someplace in between 2 and 3, but it's not an easy one to figure out. So what we can do is we can change this into log equations and then go ahead and solve it that way by plugging stuff into a calculator if we have to get a decimal approximation. So I'm going to show you how to get the exact answer, which again doesn't really have a lot of meaning to a lot of people, and then we're going to get a decimal approximation, which will have much more meaning. So we want to get the x out of the exponent, which means we want to create a log. So we're going to write the log. Remember that the base of the exponential is the same thing as the base of the log. The base of the exponential is the 2. It's the thing that you're raising something to a power of. So it's base 2. Remember that a log is an exponent. So we're going to set this equal to the exponent, which is x, which means that the 5 has to be the argument of the log. That's what we're taking the log of. So x then equals the log of 5 base 2. That is an exact answer. Okay, you have solved for x. The problem is, again, that doesn't really mean anything to most people, especially if you're trying to tell them, well, we know it's got to be someplace in between 2 and 3. How do I know that the log of 5 base 2 is between 2 and 3? You can use your calculator. If you can do the log base and do log 5 base 2. You can use a change of base formula. You can write that as the log base 10 of 5 over the log base 2. You could do it with the natural log 5 over natural log 2. And then you can plug it in and get a decimal approximation, which indeed is in between 2 and 3. It actually ends up being 2.322 as an approximated value. So, very important to understand, this is exact. It is not an approximated answer. It is an exact answer. You will be asked to give exact answers. This is a decimal approximation, which has more meaning, but it is an approximation. It is not an exact answer. So when you're asked for an exact answer, give the first one. When you're asked for the approximation, plug into your calculator and give us a decimal approximation. Okay, that's hopefully not too difficult to see. Let's do one more of those. Why not? Extend this just a little bit. There we go. So we'll do example B. This will be 8 times 3 to the x equals 5. That is an equal sign, believe it or not. All right, one of the reasons I want to show this specific example is this is not the same thing as 24 to the x. Remember, order of operations still applies. I cannot multiply the 8 times the 3 because the 3 is being raised to an exponent. Technically, the exponent would have to be done first. Since we don't know what the exponent is, you cannot just multiply the base of 8 times the base of 3. It doesn't work like that. If they were both raised to the x, then you could do that because that's a different story. Then the exponents are the same. Becomes like terms. But we don't have that situation. So, only thing to do is to divide both sides first by the 8. Isolate the exponential function. So we're going to isolate the exponential by dividing both sides by 8, which will give us 3 to the x equals 5/8. Now we can change this into a log, just like we did before. Log, let's see, the base here is 3. It's the base of the exponential. A log equals an exponent, so that's x. And then that means the argument of the log is 5/8. Again, I can take that argument because it's not 0 and it's not negative. That's the exact answer. Log of 5/8, base 3. If I want the decimal approximation, I'll just do the natural log this time. The natural log of 5/8 divided by the natural log of 3. Just make sure you plug this into your calculator correctly. And that will give you an approximated value of negative 0.428. Again, practice plugging this stuff into your calculator to make sure you guys can get the actual values here. So there is your approximated value. All right. The next one we're going to do is going to be a bit longer. It's going to be a bit of algebra, that's for sure. And that will likely be the last example that we do on this video. If you can handle this one, we can handle anything. I hope. So this will be 5 to the x minus 2 power equals 3 to the 3x plus 2 power. All right. In order to do this one, we're going to have to utilize a property that we haven't really dealt with yet, but it's still basic algebraic properties that says whatever you do to one side of an equation, you have to do the same thing to the other side equation. Okay, as long as it's mathematically applicable, we can do this. So what we're actually going to do is we're actually going to take the log of both sides. What does that mean? In its simplest form, it literally means I'm going to write the log out in front of both of the left side and the right side of the equation. We're actually taking the log of both sides of the equation. I'm going to write it as the natural log of 5 to the x minus 2 equals the natural log of 3 to the 3x plus 2. I've taken the log of both sides. We're allowed to do this because it's algebraically going to keep it the same. Same thing to one side as the other. The purpose for doing this is because now I can actually use properties of logs and bring those exponents out to the front. Okay, the bases of the original exponentials were not the same, I couldn't make them the same, so there's no way I could make that a simplified equation without doing it this way. So now I'm going to bring the x minus 2 out to the front. I'm going to keep it in parentheses just to make sure that I remember I'm going to have to distribute. I'm going to bring the 3x plus 2 out to the front of the natural log of 3. Again, keep it in parentheses to make sure you don't forget you're going to have to distribute. So now what I have is x minus 2 times the natural log of 5 and 3x plus 2 times the natural log of 3 on opposite sides of the equal sign. We're going to distribute the natural log of 5 to both pieces. We're going to distribute the natural log of 3 to both pieces. So when I distribute the natural log of 5, it's going to give us x times the natural log of 5 minus 2 times the natural log of 5 equals, we'll distribute the natural log of 3. So that's going to give us 3x times the natural log of 3 plus 2 times the natural log of 3. Okay, now what we actually have is we have a way to solve for x. I can get all the terms that have x to one side, and I can get all the terms that don't have x to the other side. So that one's got an x in it, that one's got an x in it. The other two do not. So I'm going to subtract the 3x ln of 3 on both sides. So I've got x ln of 5 minus 3x ln of 3. All I do is I subtracted that term to both sides. I'm going to move this one now to the right. So I've still got the 2 natural log of 3 on the right-hand side, but now I'm going to add 2 natural log of 5. What that now allows me to do on the left-hand side, because I have an x in common, I can factor it out. We'll take the x out to the left. That leaves me with the natural log of 5 minus 3 natural log of 3 equals 2 natural log of 3 plus 2 natural log of 5. The last step to solve for x is to simply divide by everything that's in the parentheses. So x will now get 2 natural log of 3 plus 2 natural log of 5 divided by natural log of 5 minus 3 natural log of 3. Remember that none of this stuff cancels out because these are sums or additions in the numerator and denominator. I don't have anything in common in all the terms. There's technically 4 terms there, so nothing will cancel out. About the only thing we can do, and it's perfectly fine to do this, is to simplify the logs if we wanted to by condensing them or bringing stuff up as far as the coefficients, bringing them up as exponents. It is really not necessary to do that. So this is a perfectly acceptable answer. I would leave it like this as an exact answer. If you want to plug that in your calculator just to see what's going to give you, I can tell you that that works out to be about 3.212. Again, I am much more interested that you can give me exact answers because that's actually showing me that you can do the math as opposed to just plugging a bunch of stuff into a calculator. All right, that is plenty long enough for this video. That finishes up that particular section. We will come back, and in the next section, I'm going to combine a bunch of sections into one. It's a bunch of applications. I'm going to be very choosy on which applications I choose to do. So I'm going to basically combine the last few sections or last few units of Unit 7.